previous parts of this lecture, we made a brief introduction to optimal control, and then we have learned how we can form an optimal control problem. And in this part of our lecture, we are going to dig deeper on how we can solve basically optimal control problems. But before going deeper in this direction, I would like to stop here for a while and try to give you the broader perspective. And this basically includes two main aspects in terms of control. You have probably have heard about these topics in the previous lectures, but I would like to repeat it one more time. So basically, when we have the process, there are two main options. The one is that let's assume that we have this optimal controller, and then this means that we have designed this optimal controller with respect to the let's say requirements coming from this process, and we apply the control law to the process, and this process creates an output value for us. So as you can see, this is an open loop system because there is no feedback loop that feds the output back to the controller or any other place. And as it is, this can be named as the optimal control, open loop control. If we close the loop here, this becomes as the closed loop controller. For example, the output is fed to the, let's say, controller back. So this creates a feedback loop. So what's the main difference between those two? And this is again closed loop. Okay, again, what's the main difference between those two? As you can see in this one, which is the open loop, the optimal solution directly relies on what's provided as a process, which is basically the mathematical model of your system, and it creates the optimal control laws and it directly feds to it. But what happens if we did not model our dynamical system in a proper way, or if it changed by time? So basically this type of controllers doesn't consider it because they only are subject to the value or information you provided to it, which is the process model itself. But in this case, in the closed loop ones, as you can see, we have a direct connection from the output directly to the optimal controller. This means that if we have a disturbance value here that somehow affects to our output, or if this process model change or structure of the process, not the model itself, but the actual plant changes, so this shows itself in the output, and we are able to track this information, and if possible, we can adjust again our optimal controller in this case. So this is a very significant difference. Within the scope of this specific lecture, we are going to focus more on these open loop solutions, but in the next lectures, we are going to step in this closed loop control in terms of optimal control, and this will show itself in the form of model predictive control. I would like to step in the solution approaches for the optimal control problems. But at this point, I would like to note that most of the time, creating analytical solutions for these kind of problems are quite hard to get analytically, or let me say, requires extensive tools or so. But of course, we also have something in hand. Something in hand means mostly the necessary conditions. So it's because of that, firstly, I'm going to define an optimal control problem and provide you the necessary conditions, so which solves itself as the Euler-Lagrange equations, and sometimes could also be named as the Pontryagin's maximum principle. Okay, so then let's step in and formalize the main type of problem that we are going to deal. So let's assume that we have such an optimization problem. Okay, so this is our objective function, and subject to our system model and the initial conditions of the system as given, and some, let's say, terminal constraints that shows itself in the form of like that. So as you can see, we have briefly introduced this formation of an optimal control problem, Here we have the objective function. Here we have our system model, which is a nonlinear model in this case. And here we have the terminal constraints. I would like to note that this is just one type of optimal control problem. So there are various options or possibilities here. For example, TF, the final time, is fixed at this formulation, but you as a designer or engineer can also take this final time value as a parameter. But of course, in that case, the type of the problem will change, and the things that you need to do to solve this problem will also change. Another thing that I could note at this point, for example, you don't have any path constraints here. So if we have these kind of additional constraints here, let's say, the structure of the solution may change slightly, but I think this example is generic as possible so that we can touch the main principles of important parts of the solution strategies. And as a solution strategy, I should also note that I'm going to provide you the necessary conditions first. These necessary conditions you can interpret like, for example, you have a polynomial equation and you would like to find the minimum and the maximum of it. What you need to do is to first take the first derivative of it and find the stationary points. So you can set an analogy like that here. Okay, in order to derive the necessary conditions, first we need to define another type of formalism here, and this is named as the Hamiltonian of the system here. And Hamiltonian is defined with the H letter here, and it's a function of x, u, lambda, and t. And by definition, it can be written as something like that. Okay, so let's stood here for a while because there's too much equation on the board at the moment and try to understand the meaning of those. As you can see, there is only one extra term at the moment, which is lambda. I will come to that point, but the other things is already we have in hand. For example, this L here is already the thing that we have here. And this F function is also another known, let's say, function, which is this one. And this lambda phi is named as the Lagrange multipliers. And this whole thing is named as the Hamiltonian. So it may sound a bit abstract at the moment, but we are going to use this H term, Hamiltonian, directly in order to derive the necessary conditions. And let me then write them directly. Okay, so these are the necessary conditions, and sometimes they are also called as Euler-Lagrange equations. As you can see, we have this one. I'm sorry, there should be a dot here. We have this one originally from the problem formulation, which is this one here. And the rest is basically we use to derive the optimal U control value. So, for example, this provides M algebraic equations. This one provides N differential equations. And again, this one provides N differential equations. So this means that we have 2N equations in hand, and in order to get the solution for this, we also need at least 2N boundary conditions for that. And with respect to the Pontryagin's maximum principle, we are also able to derive these conditions. I am also going to write this down here. Okay, so the last term here is comes the final time constraint of lambda t, which is the Lagrange multiplier. So we also have this phi, and we also have this g function here. We can evaluate this equation and assign t to the tf, and then get the n additional boundary conditions. So as you can see, we have n equations coming from boundary conditions coming from here, and boundary conditions coming from here. We have this additional term v here, and this in order to tackle with them, we also have Q-side equations here. So as it is, this also gives us, let's say, all the things that we can go for the solution. And this is named in literature as two-point boundary value problem. So this is more or less all regarding with the formulation of a Pontryagin maximum principle. Sometimes it's also called as Pontryagins minimum principle. But to be honest, deriving the analytical solution most of the time is directly related with the complexness of your problem in hand. For relatively simpler questions, it's directly possible to derive analytical solution, but when the scale of the problem increases, it becomes harder to get the analytical solution. It's because of that researchers and scientists also look for some other approaches where they can combine this already existing information and the computational power in hand to derive the satisfactory results in terms of optimal control. So, due to the complexity of most optimal control problems, it's not always possible to get the analytical solution directly. But of course, we have still have something to do with it. So, there are some available approaches proposed in literature. For example, the dynamic programming, which was initially or based on the optimality conditions of Richard Bellman. But to be honest, this approach didn't find too much application areas in terms of practical engineering fields. It's because of that today we are going to focus two other main approaches, which can be named as the direct methods or indirect methods. So these direct and indirect methods basically differentiate from each other at which phase of the approach the discretization is done. So by discretization, I mean we have an infinite dimensional problem in hand at the moment, and we are aiming to, let's say, divide this into subspaces so that we can look for, let's say, optimality within these subspaces, and then by merging them together, we have, and let me say, we can derive good performances and close to the optimality. So within the scope of direct methods, the main intention is the first to discretize and then optimize. So this means that we have an infinite dimensional problem in hand at the moment, but then we are cutting this whole, let's say, time frame into subframes, and then we are optimizing each single subframe, and we, let's say, merge the overall results. And in the indirect methods, it's slightly different. In these approaches, first it's used these necessary conditions for optimality, and the equations that I have showed before is considered, and an iterative approach is required to solve this two-point boundary value problem, which, let's say, complicates the things. But on the other side, in the direct methods, after discretizing the first problem, it is converted to a nonlinear programming problem, and then by using the available tools in hand, which means that nonlinear programming solver, we can get the solutions, optimal solutions for that defined frame. And of course, these two approaches have some pros and cons. So advantage of the direct method is the solution can be derived quite fast, which is a nice thing. But on the other side, it's hard to prove optimality. So this means that we probably have still a satisfactory result in terms of performance or so, but from the analytical perspective, it's hard to prove the optimality. And on the other hand, in the indirect methods, as a kind of advantage, the optimality comes as a built-in property for this. So as a kind of disadvantage of the indirect method, so it's challenging, and sometimes it's really slow to get a result that is converging. So all in all, we have these two main approaches, and with respect to the considering their popularity, today we are going to dig a bit deeper into these direct methods because they find more application areas in most of the engineering fields. So the direct methods can also be subcategorized, and these show itself in the case of control parameterization or state and control parameterization. So control parameterization is basically relies on your control parameter. Let's say that you have the temperature as a control parameter and you are aiming to define the whole range starting from T0 to Tf into some subparts. And of course there are also some several approaches here, like the control vector parameterization and the single or multiple shooting. So they are slightly different from the conceptual point of view, but today we are going to dig deeper into the control vector parameterization, which I'm going to provide you further details on this. But in addition to this, we can also, let's say, discretize the states. But of course, not the states themselves only. We should also consider the control parameterization here, and it shows itself into this area, and there are some local and global approaches which is indicated like this here. So today we are going to continue with the control vector parameterization. So the discretization approach brings us quite lots of benefits in this case. For example, here I have prepared a sketch for you. So in the upper one, we have this optimal control profile. So the rest is a bit exaggerated, so they need to converge to the optimal profile. But in order for you to understand it better, so I just sketched them on the below part. So in the case of discretization, the first thing that we need to do is to divide the whole time frame into, let's say, sub points, like let's say starting from T0 to Tf. This could be T1, T2, T3, etc. So this spacing can be uniform or non-uniform. So this depends on the designer or type of the problem some of the time. So, but you have these kind of options here. Then, so as you can see, we have an infinite dimensional problem or solution profile here, and it's not directly possible to get this profile all the time with analytical approaches. But what we are trying to do here is to cut this whole time frame into subdomains and then use some certain profiles within these ranges. For example, in the first one, we have piecewise constant. As you can see, the input profile doesn't change. I mean, within a specific time frame, the input profile doesn't change. The only change happens when we are jumping in another field. And another thing that I could mention here is that, for example, this one is a linear curves composed of linear curves, but with the continuity conditions. Continuity condition may be important sometimes because it's related with what kind of input variable do you have in hand. For example, if your input is a continuous signal, let's say the temperature signal, then it makes no sense you choose a piecewise constant profile because the temperature may not jump from the same time point. Then you need to select the continuous profiles like this piecewise linear or piecewise polynomial or some other that fits into your scope of problem. But these are the things that we have in hand. For example, this is the piecewise linear without the continuity condition, and for example, we have here the polynomial approach, again without the continuity, and the last one here is with the continuity condition and the polynomial approach here. So this is what is, let's say, created on the background in terms of discretization. And then the optimal control problem needs to be sequentially solved for each of these time frames, and at the end of the day you get a combined solution. So, and hopefully the solution that you derive is converging to the optimal one. Of course, this is strongly related with the way that you chose, that you create this discretization. So for example, when you narrow down the time steps here, so with high chances you can get a better results. So in this way of discretization, so in terms of formality, our optimal control problem may slightly change. And for example, here you see the above is more or less the same. Of course, with some selections, there could be some other constraints here. But we are also introducing the set of inputs here. So U1, U2, UN. And this is directly related with the type of discretization that you applied for your problem. And of course, after that discretization, you're going to need solvers to, let's say, handle this computationally extensive problem. And luckily, there are lots of available tools in hand that you can find also on internet. And I would like to name some of them here. So, for example, Akado or Synopt or Dido. There's also Mädler extension of this, and then Amigo too. So these are some of the available, let's say, toolboxes in literature, but of course they are not the only ones. And you can basically use any of them to get your solution. By the way, I should also note that the optimal control toolbox of MATLAB is quite extensive, and you can also do lots of things with only using the optimal control toolbox of MATLAB. So exercise questions regarding with the theoretical things that I would like to introduce, that I have introduced here, is also provided to you. And I strongly advise you to have a detailed look on the exercises. There you can also find some solution scripts so that you can dig deeper into this concept. So all in all, today we have introduced the optimal control problem formulation. We have, let's say, tried to point out the importance of it, and also discuss the main solution strategies, which is direct and indirect approaches. And discretization plays a crucial role in direct approaches, because the way that you discretize the system is strongly related with the performance that you may get at the end. And of course, we also briefly mentioned about the available tools in literature where you can use as a solver for your optimal control problem. So, of course, this is not the end of the story. Today we are cutting here, but in the next lectures we are going to continue with the model predictive control approach, and also for the linear and nonlinear systems. That is also playing a quite an important role in the control domain, because they also let you to react to perturbations or disturbances that's applying to your system. So, but that's all for today.